Hi, this is Devin Coughlin, that's me, and I'm giving a screencast version of my ISSTA 2012 talk, Measuring Enforcement Windows with Symbolic Trace Interpretation. This is joint work with my advisor Evan Chang and with Jeremy Siek at the University of Colorado at Boulder, and with Amer Diwan at Google. This work is motivated by the problem that static analysis design is expensive. And one reason it's expensive is that once an analysis designer has a great idea for a new design and has worked it out on the whiteboard, they then have to implement it to make sure that it's sufficient on real-world programs. Here, by sufficient, we mean that it proves the property of interest, say that the program is free of null pointer exceptions, with an acceptably low false alarm rate. Most of the time, it isn't the first time through the cycle, and the designer has to repeat it again and again. This can take months or even years to arrive at a sufficient design. We want to help improve this process. What static analysis designers really want is a sufficiency oracle that can tell them if their design is sufficient without actually having to build the prototype. But oracles are hard to come by, so we don't do this. Instead, we help them shorten their cycle with data. The idea is that if we can inject data into the design cycle early enough, they can rule out insufficient designs early, and thus avoid having to build a prototype that won't work anyway. In this talk, we're concerned with a specific kind of insufficiency, what we call analysis scope insufficiency. We define analysis scope to be the part of the code the analysis examines to prove the property of interest. In the rest of this talk, our example property of interest will be that a given dereference will not throw a null pointer exception. A related concept is the validation scope, and this is the part of the code where a perfect static analysis can prove the property of interest. And the key point here is that if the analysis scope does not completely encompass the validation scope, then the analysis is clearly insufficient. In other words, if a perfect static analysis needs access to some bit of scope, and your analysis doesn't look at that bit of scope, then your analysis is definitely insufficient. On the other hand, if your analysis scope does completely encompass the validation scope, that doesn't mean that your analysis is sufficient, just that we haven't been able to prove that it isn't. Let me explain validation scope with an example. Here we have a program with a main method and two methods A and B, and a deref method. The deref method takes in some parameter and dereferences it. The A method passes in a constant value to deref, and the B method takes in some parameter, checks to see if it's not null, and then passes that to deref. Let's look at what it would take in order to prove that this particular dereference is not null. That'll be a property of interest. Well, if we look at B, we see that B checks its parameter and then passes it to deref. So that check ensures that S is not null. And if we look at A, we see that it's passing in a newly allocated object, which in Java can never be null. So the key point here is that main is completely irrelevant to the property of interest. That is, the validation scope includes A, B, and deref, but not main. We argue that scope is a crucial dimension for static analysis design. In particular, if the validation scope is too large, then the analysis won't be modular enough to scale to large systems. And if it's too small, then the analysis will be so conservative that it won't be able to prove the property of interest. So for example, with this particular analysis scope, an analysis would be unable to prove that S is not null because it doesn't know anything about the values that are passed in to that parameter. Really, picking an appropriate validation scope is essential to static analysis design. So how do we pick an appropriate scope? Well, we define validation scope as the part of the code where a perfect static analysis can prove the property of interest. And this perfect, you might think this is a problem, that we've defined ourselves into a corner. Because if we had a perfect analysis, we would be done. Of course, no one has a perfect analysis. Our choice is to use dynamic analysis to under-approximate the validation scope with what we call a dynamic scope. And the key idea here is that if an analysis scope does not include any part of the required dynamic scope, then that's an indication that it doesn't include part of the validation scope and is therefore insufficient. Let me explain dynamic scope with an example. So this is that same bit of code, and if you recall, when I talked about validation scopes before, what we were really interested in was how two different values flow through the program, high and by. Let's consider high first. It's established to be not null in the A method, and that's then passed into deref, where it's used. This means that the dynamic scope for that particular value includes A and deref. Then, for the by value, it's initially established in the main method. It's then passed to the B method, which compares that value to null, and then passes it to deref where it's used. In this case, the dynamic scope includes only B and deref, because it doesn't matter, the check makes it so that it doesn't matter what happened in main. The union of these two observed value scopes is our dynamic scope. And if we could get it, the union of all such value scopes would be the validation scope. We call this sequence of establishes, checks, and uses an enforcement window. And it's important to point out that our technique is not limited to just null pointer analysis. So for example, for downcast checking, an establish would be an allocation, just like a null pointer analysis. A check would be an instance of operation, and a use would be a downcast. The key thing here is that the dynamic path that the value takes from the last check to the use under-approximates the validation scope. Now, a natural question for any under-approximation is, how under-approximate is it? Does the dynamic scope look like this, or more like this? To investigate this question, we first have to define another kind of scope, what we term the bottleneck scope. The bottleneck scope is the scope implied by all paths from the last check site to the use site in the static control flow graph. This static property means that it's an over-approximation of the validation scope. But because the dynamic scope is an under-approximation of the validation scope, if we can show that the dynamic scope is a bottleneck scope, then the dynamic scope equals the validation scope. To find out how often this happens in the real world, we ran a static bottleneck analysis on the Takapo benchmark suite, and we found that 51% of the time, dynamically observed use sites are bottlenecked by observed checks in a single execution. This was surprising to us, because as we said, the bottleneck property is an all paths property, and that's not something you typically expect to see in a single execution. We hypothesized that perhaps for a given use site, the same enforcements are used in all executions. This might explain what we see. In any event, what this means is that generalizations from dynamic scopes are likely to be helpful. So how do we actually find dynamic scopes? We propose a dynamic analysis technique called trace interpretation. Trace interpretation takes code and instruments and executes it to produce a rich trace of instructions of interesting things going on in the program. We can then interpret those instructions with an alternate semantics to capture the scope. These alternate semantics, in addition to capturing scope, also allow us to do two interesting things. One, we can measure the complexity of the required analysis reasoning for a given scope. And two, we can simulate static reasoning when capturing a scope. To measure the complexity of the scope, that is, how hard it is for an analysis to analyze a dynamic scope, we need some kind of metric to measure the scope. But what metric should we use for complexity? In our paper, we define 4 different metrics, but in this talk, I'm only going to focus on one, and that's the inlining depth metric. The inlining depth metric characterizes the complexity of a dynamic scope in terms of the number of inlinings required to bring the path that the value takes from the last check, or the established, because an established can be viewed as a check, to the use, all into one method. So, for example, if a value is checked in A in this call tree, and then returned to B, which then passes it to C and passes it to D, then the inlining depth required is 2. One level of inlining to inline D into C, and another level of inlining to inline A and C into B. This is a particularly useful measure of scope for context-sensitive analyses, and in particular, inlining depth is essentially K in a K-call strings-based analysis. So how do we actually get these inlining depths? Well, as I mentioned before, we have an alternate semantics that, when we interpret the trace, performs these measurements. Here we have alternate values, where these values are pairs of hmin and hmax, which are the minimum height and the maximum height that a value is exposed to as it travels through the program. And then our interpreter will store these alternate values in memory locations in our interpretation state and update them as we interpret the trace. Let me walk you through this. So for our value that was checked in A, that check causes the measurement for A to be 1, 1. We say that the checked value has been exposed to a minimum stack height of 1 and a maximum stack height of 1. Then when it's returned, it's exposed to a height of 0. So its alternate value becomes 0, 1. When it's passed to C, it still hasn't been exposed to anything higher than 1, and so its value stays the same. But then when it's passed to D, it's been exposed to a stack height in the call tree of 2. This updates its value to 0, 2. Then at a U site in D, the inlining depth is given by hmax minus hmin, which in this case is 2. For any alternate semantics, there's two key parts: the measurement domain, in this case the pair of min and max, and the transfer functions, which for a given trace instruction tell us how to update measurements. You can see our paper for our other metrics and the semantics that we define for them. The other problem that trace interpretation solves is that dynamic analysis can be too perfect. Let me give you an example of this. Here I have two methods, a caller and a callee. And the key thing about this example is that the callee takes two parameters, and the callee passes the same value, high, into both of them. And then the callee checks one of its parameters and then dereferences the other. In a perfect dynamic analysis, the system knows that A and B are really the same value, high, and so a check on A counts as a check on B. But this is clearly misleading because it exposes aliasing relationships that static analysis cannot know locally. Our solution to this is to not do concrete trace interpretation, but instead make it symbolic. This allows the analysis to forget concrete aliasing relationships and simulate static reasoning. Let me give you an example. So here, when the caller passes in high to the callee, instead of passing in the concrete value, we pass in two distinct symbolic values, alpha and beta. And a check on alpha here does not count as a check for beta. The key thing here is that a single concrete value can be represented by multiple symbolic values. So what's really going on here? Well, we're using symbolic trace interpretation to model more realistic aspects of static analysis. The symbolic dynamic scope that we measure here is not really an under-approximation of the perfect validation scope. It's under-approximating something else. Some partly realistic validation scope. This allows us to evaluate analysis design choices in isolation. So, for example, we could answer the question, assuming perfect control reasoning, is alias analysis insufficient? So we have this tool for measuring enforcement windows and scopes. What kind of data does it give us? We've performed two experiments with our tool, and we wanted to use it to find out what scopes look like in real programs. Two experiments that we looked at are, one, how big are validation scopes in real-world programs, and two, how the validation scopes relate to bug fixes. To look at real-world programs, we took the decouple benchmark suite and ran our tool on it. This graph here shows the cumulative distribution of dereference sites that have a given inlining depth distance. So, for example, for the bloat benchmark, which is marked by the downward triangle. 40% of dereference sites required an inlining distance of 0, and 80% required an inlining distance of less than 50. There's really two interesting things going on in this graph. The first is that most sites require small analysis scopes. And the second is that a not insignificant fraction require Herculean analysis scopes. This gives empirical evidence supporting the conventional wisdom in static analysis that handling most cases is very easy, but handling all is very, very hard. In our second set of experiments, we mined software repositories for real bugs to try and answer the question, how do scope sizes relate to programmer bugs? So we looked at two open source projects, PMD and Lucene. PMD is a programming mistake detector that takes in Java source code and tries to find simple errors in the program. And Lucene is a widely used search and indexing tool. Our first experiment in this case study was to troll the project issue queues to find revisions with null pointer exception bugs, and then to compare the distribution of the scope sizes for buggy sites and non-buggy sites. And we found that buggy sites had larger scopes. This is perhaps an indication that programmers have a harder time reasoning about large scopes. In this talk, I'll just give the conclusions that we draw from our experiments. The full data is available in our paper. We were also interested in how scopes change after fixes. So we measured the buggy site scopes immediately before a fix and after a fix. And we found that fixes make scopes smaller or keep them the same size. And that when they get smaller, they usually go completely local, that is, with an inlining depth of 0 into the same method. That means that most of the time, programmers are applying fixes right at the source of the error, and not higher up in some different part of the program. We were also interested in measuring the difference in the distribution of scope sizes as programs change. So we looked at PMD and Lucene as they more than doubled in size and over a span of years. And we found that scope sizes remain remarkably stable as programs evolve. This was not what we expected. Our hypothesis was that we should see smaller scopes as programmers adopt defensive programming techniques to deal with the growing complexity in the projects. What's interesting about all these three results in the case study is that we had hypotheses about what we would expect to see, and our tool let us validate or refute those hypotheses. In conclusion, I would like to say that dynamic analysis is remarkably effective at finding enforcements, perhaps because for a given site the same enforcements are used on all executions, and that measuring enforcement windows gives static analysis designers a tool for data-driven analysis design that helps them detect insufficient early and confirm or refute folk wisdom about programs.